in the previous video. If you have any doubts, please tell me. Now in this video I'm going to just first summarize the two central ideas which we need a hold of, which we need to remember while doing any kind of application of Lagrangian mechanics. The first idea is that the variable Lagrange L is equal to T minus V for the systems we are studying, where this L is called a function which is Lagrange, and T is called the kinetic energy of the system, and V is called the potential energy of the system under study. The second central idea is that the first order derivative with respect to time, I take partial of L, the same Lagrange L, which is again with respect to some partial of Q dot J. Now in the previous video I wrote I, here I am writing J. Well, this has got to do with the notations only, and as for the matter of fact, let me tell you that this specific video is meant for applications and engineering aspects of Lagrange. So in engineering we use J as a subscript for various quantities, and that is basically a tradition used in the field of engineering, but in classical physics and mathematics we use I as a subscript. So basically they are the same, they are just signifying the finite integer, that n. So J belongs to some finite integer n. Now the thing is that this thing has a dot, so Qj dot, basically the Q is again that same generalized coordinate Qi, which I am going to discuss today in this video, and the first order derivative of that equals some capital Qj. Now what is this term, new term? I'll tell that, plus partial of L with respect to partial of Qj. Look at this equation carefully. This is a new equation, the same Euler Lagrange modified and revamped to be applicable in this engineering dynamics. So how do we apply this for mechanical systems? In mechanical systems there are pulleys, rods, strings, masses, and they do not involve any kind of idealizations. Friction might not be zero, air resistant might not be neglected, many things might or might not happen, and accordingly Lagrange is a powerful tool to handle gangsters like friction. Even friction will not be a blockage to our procedure so far mathematically also, because this Qj takes care of that, and I'll tell exactly what means what in this equation. So basically this is the modified form of Euler Lagrange. Basically you have noted that this Qj, capital Qj term, was 0 in the previous equation I wrote. That was the mathematically elegant form of Lagrange in a very compact form, and that was idealized for conservative systems where all forces are conservative. But this one is idealized for far more general case where non-conservative might act. If the system is said to be conservative in the problem, you simply make this Qj term 0. So the simple equation remains that same happy like it was the day before. Now when I say that Qj, it means it is generalized coordinate. Now what I exactly mean by saying the generalized coordinate, I'm coming to that point now. The other term you saw, this Qj, this means generalized force. This is generalized force corresponding to the generalized coordinates we are using, and these two are important in our Euler Lagrange modified. Now see something. Now we know the central idea that L is equal to T minus V. So when we make a substitution in our Euler Lagrange, you saw that d by dt of L with respect to Qi at Qj dot, that was equal to partial of this L with respect to partial of Qj. So there, that L is replaced with this T minus V term. I am replacing L with T minus V in our Euler Lagrange equation. So what will happen? We are getting d by dt of partial of T by partial of Qj dot minus, I'm simply substituting L in our Euler Lagrange. minus dy dt of partial of the potential of the system by this stuff qj dot first order derivative of generalized coordinate minus partial of t with respect to partial of qj. This is very simple, you will get this result only if you do it yourself. And then we have this partial of v added to this expression like this. This is what it points down to, and that is equal to qj. Basically I have substituted L with T minus V, and this is what you get. Now we are dealing with mechanical systems. We are engineers. We are not interested in elegance of mathematical equations. They might not be compact for our purpose. What should serve our purpose as engineers, you can say, or as practical experimental physicists, is that all our equations must talk. They must speak volumes about how useful they are in terms of the real world. So since we are dealing with mechanical systems where potential energy of our system is not a function of velocity, or it is not even a function of time, you might have never ever encountered any such potential energy for macroscopic mechanical systems where your potential energy becomes a function of either velocity or time. You might say, what does that mean? I will say that, at the microscopic atomic level where you deal with the motion of electrons, there you might say that the potential depends on the velocity, on the force, on the time. But here in our mechanical systems where we are dealing with masses and pulleys, there is no involvement of any kind of such potential energy which is a function of time or velocity. But in our previous expression we got one such term which was d by dt of, if you remember correctly, it was d by dt of this partial of v with respect to partial of this term qj dot. It's going crazy today. You got this term, right? What does this mean? This is the first order derivative of partial of v with respect to this one. Now the thing is that this v is meant for mechanical systems. It cannot be a function of this time, so we cannot differentiate it with respect to time, and this will not interfere in any operations of this derivative over this quantity. The del has got nothing to do with that. It simply means variation of potential energy. In simple words, this is zero, because for mechanical systems, that this potential energy is not a function of any kind of velocity or time. So therefore we cannot differentiate this expression with respect to dt as our reference. So this becomes zero for mechanical systems. So what does that mean? So our equation turns out to be dy dt of del t by del qj, right, minus that v dy dt of del v by del q dot j that got eliminated for mechanical systems only, and we are getting this. This is equal to this qj. I name this expression as 1, this expression as this one as 2, this one as 3, and this one as 4. It looks like a 9. It's a 4. You know that this equation is exactly what is useful to a physicist or an engineer, that this thing is equal to qj. This equation is what is used as in for Euler Lagrange. We do not use that dy dt of partial of L with respect to some partial of some generalized coordinate first order derivative. We do not use that L as our term, so because that is not of much physical significance. As I mentioned, what is of physical significance? Kinetic energy, potential energy, forces. These quantities make sense to us physicists, to us engineers, not for mathematicians perhaps, so those fools use I hope you didn't heard what I said. Yeah. So they appreciate and sit all day long to appreciate the elegance and beauty of equations, and they are quite satisfied with our uh, compact equations maybe. So anyway, this is 1, this is 2, this is 3, and this is 4. Jokes apart, this 1 2 3 4 remembering helps us because engineers need to be fast and accurate, and Euler Lagrange is to be used by engineers in a way that it makes sense physically. We cannot deal with mathematical beauty. Now, what I mean is that it makes it way more practical to use in real world problems where you are not allowed to actually use the equation in its crude form. Who will give you pen and paper? You simply need to compute things very fast and get results which are damn difficult from Newtonian mechanics, because he did things by observing, but we are doing things from the mathematical point of view. We are using mathematics as a tool. Now let me tell the main central idea of this video. So what do we mean by generalized coordinates? Our QJ here represents generalized coordinates. This has gone crazy. Generalized coordinates. What do I mean by that? Coordinates. What are these generalized coordinates? What exactly do they mean? Number 1. So generalized coordinate, what does this generalized mean? It means something general, which means not necessarily something particular, right? Without any loss of generality, which means not necessarily Cartesian. These coordinates might not be Cartesian. So not necessarily Cartesian. That is what I mean by generalized. Not necessarily Cartesian, which you are familiar with from your coordinate geometry knowledge. We deal with Cartesian equations, Cartesian coordinates, Cartesian planes, but this might not be Cartesian at all. It is not necessary. It can be, but it cannot be. All depends on a few tests which you need to perform. So number 2 is that not even inertial. They might not be inertial coordinates. Not even inertial. It's a very general formalism. Number 3 is that must be independent. I'll tell what we mean by independent in this context. Must be independent. The generalized coordinates should be independent. There is some definite meaning to that. And number 4 is that they must be complete. Number 4 is that they must be complete. I will say what I mean by complete, what I mean by independent, what I mean by not even inertial, or what I think I have said this meaning. And the fifth condition, perhaps the most important, the deciding factor whether we will apply our Lagrangian approach or not, that fifth condition is that a coordinate you choose is said to be generalized if by choosing that coordinate your system must be holonomic. Holonomicity is a very important condition which needs to be satisfied. I'll tell what holonomicity means. System must be holonomic. What I mean by the property of holonomicity, well, it is a very simple concept. The name is just a tech savvy terminology given by engineers, so it is holonomic. You have to check for a given system, if the system has got coordinates, you will choose coordinates to solve problems. The coordinates you have chosen will be generalized if they pass the test of being independent, if they are complete, and if the system becomes holonomic, which means, now I'll go word by word. Independent. So what does that independent mean? Independent, I'm not writing it. We do not write independent with I. I'm just simply writing I to make you understand. So when you fix all coordinates, but you keep one coordinate free for your system, and for that one coordinate, the system still has a range of continuous movement in that free coordinate. So it might turn a bit theoretical, but let me take the example of a double pendulum. This is a rigid support. this is how a double pendulum looks like. There is a mass bob and there is another bob attached to it. So basically this is one bob, and then we have some string like this, and this has got another bob. Okay, let me make it a bit tilted. This has got another mass bob, maybe of different mass, of same mass anyway. So here touch screen is crazy today. Now here what we are dealing with is that, let us say this is m2, this mass is m1. This is chosen as a Cartesian coordinate, the y-axis. Let us say this is our x-axis. So to solve this problem of double pendulum, you have chosen x along this direction, y along this direction, and these coordinates which you assume to be generalized are your Cartesian coordinates. But you need to check whether they are generalized or not. How will you check? First you will ask, we have how many coordinates to describe this system? Well, for this mass bob, we need how many coordinates? 2. Let us say that this is x2 comma y2. To define the position of this bob at this particular instant of time, gravity is acting here. Okay, let this be defined as x1 comma y1, the position of that bob, this one. So how many coordinates do we have to describe completely? We have 4 coordinates, 1 2 3 4 4 coordinates to describe this system. But this system has 2 degrees of freedom. You know, it can oscillate like this and it can oscillate like this. By which I mean, after fixing coordinates, you are restricting its motion to oscillation. And it is quite common that systems might have oscillations of some degrees of freedom. Systems might need some amount of these coordinates to describe them. And we relate these two quantities by what is called holonomicity. Idea is very vague, but I'll go to that in detail. But first let me deal with how do you test whether your coordinates are at all independent. So what I mean by independent is that, basically I said that, what is the meaning of independent? When you fix all the coordinates, but you keep one coordinate to vary. That one coordinate has some variable value. It can assume values. So if that happens and the system still has a range of movement, continuous movement along that free coordinate, then the system is said to have independent coordinates, and that satisfies one of the first conditions of being generalized coordinates, by which I mean here, if you fix x1, if you fix x2, if you fix y1, but you keep y2 free, if you keep y2 free, you have fixed 3 variables. Let us say x1 is 1, y1 is some 3, so this mass bob is at a position of 1 comma 3, and this is fixed at some other position, let us say some 7 comma y2. Now do you think will this system move at all? Well, this system will freeze. Keeping y2 free is not allowing the system to move along y2. How will it move? You have fixed 3 and you see this whole system freezes. Motion is ceased. It is not possible to move. Like, this will not be independent coordinates. So this is the meaning of independent coordinates. Now what do I mean by independent coordinates in this context of double pendulums? Well, let me tell you that in this case of double pendulums, let me draw this properly. In this case of double pendulums, what are our independent coordinates? Give the video a pause and think about what type of coordinates do you need to choose that they become independent of each other. I hope you are back and you have thought of that. Let me draw the pendulum meanwhile. Think, what type of coordinates do you need to choose in this double pendulum which make them independent, and it is making it a first step towards generalization of coordinates. Think about that while I am drawing the diagram. It is clear from the previous context that Cartesian coordinates are not independent, because if you fix any 3, the other one made free is not contributing to any motion. the system freezes, right? System won't move at all. Think about it. Anyway, I'm telling it, I'm drawing it. So this is our fixed ceiling, and this was okay. We are not choosing Cartesian anymore. This is one of our mass bulbs. This is another mass bulb with a string, and let us say this one has got some mass m2, this one has got a mass m1. Gravity, this guy acts downwards, this guy is downwards over here. Anyway, we are not concerned about forces, but now you can imagine that, let me draw the perpendicular. So you can take this as a coordinate phi 2. Let us name this angle as phi 1. Now you tell me, if I take phi 1 and phi 2 as my generalized coordinates, set of generalized coordinates, do they satisfy the condition of independency? Like if I fix phi 1, will the system freeze or will it still have motion in the direction of phi 2? Yes. If you feel, if you fix this phi 1, you visualize this, you have fixed phi 1, this can still oscillate. If you fix phi 2, even this can still oscillate, this m1 can oscillate, which means phi 1 and phi 2 are independent. There will still be some motion, some oscillatory motion of m1 even if phi 2 is fixed, and vice versa, which means these qualify the first step towards generalization. They are independent. But notice that these are not Cartesian, right? These are angular coordinates, for that matter kind of polar coordinates, similar to polar coordinates, but here our generalized coordinates must be phi 1 and phi 2 if we are to solve this type of a problem using Lagrangian, because they are the first step towards being generalized. We need to have to do some other kinds of tests also. Apart from being independent, there are many other conditions to satisfy. Now what do I mean when I say the coordinates must make the system complete? I said the system must be complete by using the chosen coordinates. So what do I mean by being complete? Well, complete in this context means capable of locating all parts of the system at all times. The coordinates must be chosen such that they are actually capable of locating all the parts of the mechanical system at all times, at any instant of time, in fact. That is the meaning of complete. And what do I mean by holonomic? It's very easy. A system is said to be holonomic if the number of degrees of freedom, I denoted by hash DOFs, the number of degrees of freedom of a system is equal to the number of generalized coordinates you have chosen. To completely describe the system. This is the condition of holonomicity of a system. Suppose a system has 1 degree of freedom, a very simple system, and suppose it happens that to completely describe that system you choose 1 coordinate. So number of degrees of freedom of that system equals the number of coordinates you have chosen to completely describe that system. For that matter, this system becomes holonomic, and therefore your coordinates become generalized. This is the final test of generalization of coordinates. Your coordinates are generalized if the number of degrees of freedom of the system is equal to the number of coordinates you have chosen to completely describe the system. In that context, complete means what I said, that it is capable of locating all the parts of the system at all times. Now we have done holonomicity, we have done test of independency, we have done how it is complete. One thing I want to say is that if the number of degrees of freedom is not equal to the number of coordinates needed, then you cannot apply Lagrangian equation. This is important. We cannot simply apply that. Now, is there any systematic approach while solving any kind of mechanical system which has to be solved using Lagrangian? Is there any kind of approach? Yeah, we have a systematic approach to do so. an algorithm which you might not follow, but it is for your convenience to do problems which are beyond the scope of Newtonian mechanics. So what we do is that our approach in solving is, I'm just giving a set of algorithms, but you might or you might not prefer these, but if you prefer them, your Lagrangian approach will be simplified to a great extent. So basically, we know that if you remember correctly, our LHS was 1 plus 2 plus 3, those 1 2 3 terms, if you remember from this video. And so I write LHS, computation of LHS. How do we find the LHS of our Euler Lagrange equation? First step is determine the number of DOFs. This hash means number of DOFs, and choose a set of coordinates to completely describe the system. Number of some QJs to completely describe the system. These QJs might not be Cartesian, but they must pass your test of independency, completeness, and the system must be holonomic by choosing such QJs, and that makes the coordinates QJ, that is generalized. This is the first thing. You first determine the number of degrees of freedom, in how many different directions it can move, and perhaps the second thing you find is that the number of coordinates you are using and what coordinates you are choosing. First choose those. Second, verify if those coordinates are complete, if they are independent, and that makes the system holonomic or not. If your answer to the test of holonomicity is a no, then you cannot apply this approach. If it is a yes, that means number of DOFs is equal to the number of uh, coordinates you have chosen to describe the system, which means it is holonomic, which means you can proceed with your approach. Now the third step is basically computing T and V separately for every rigid body in the system. You find T for every rigid body in your system, add them up to get the final T. It is summation of all kinetic energies of a system. And you find the V for each rigid body in your system, add them up to get the final summation of potential energy of that system. This is very simple. This idea is from the basic physics you have learned so far. And now you simply compute. After this step, the fourth step is for LHS computation. You simply find term 1, term 2, term 3 for each QJ. Remember this, for each generalized coordinate you do this QJ. By that I mean, if you have two generalized coordinates, the whole Lagrangian process will be done twice as per holonomicity. So for each QJ you compute each 1 2 3. Now for our RHS right hand side, the first step is for each QJ, for each generalized coordinate QJ, find corresponding capital QJ if any, and that goes with it. This is source of all non-conservative forces. And number two is that this is basically a force, and number two is that computing the virtual work done by the non-conservative forces. Virtual work done, this is the sign of virtual work done, non-conservative, which is associated with the virtual displacement del Q. So basically, how do we define this virtual work done and how do we compute the RHS of our Euler Lagrange for dynamical systems is that our virtual work done is equal to this thing, the force in the direction of virtual displacement dotted with the virtual generalized displacement. This is the variation in J, along J. J is R, or you can say QJ rather. I must say QJ. I must not change the dotted with the force along J, dotted with the QJ. This is the virtual displacement. You remember this was some kind of displacement variation of the generalized coordinate. Now the thing is that after computing this step, after framing this equation, from here you get this QJ. and then you put this as your RHS and you equate it with your LHS, which was summation of, basically Qj is that fourth term which is equal to LHS, which is sum of 1, 2 and 3, and basically you get your result, which is the final equation of motion perhaps as per the system. But if no non-conservative forces are acting on the system, RHS is 0. Simply put, RHS 0. That is what we got from our first video, and that is what I mentioned there. So you have to look out for problems, how things are happening. Now the very easiest system I came across as per, and I think it is one of my favorite systems so far, is the mass spring system. Let me do it in a different color. Mass spring system, and this will be the last uh, topic of discussion in this video. In the third video, I'm going to put a few set of problems of varying degrees of hardness or difficulty, and mainly they will succeed in the level of difficulty as the problem goes. I think I will do three selected problems. And for Lagrangian mechanics, you can follow up more from this by from book which I studied, which is Introduction to Mechanics, Classical Mechanics by Kleffner and some Kloffenklau, something was there, some Russian name I guess. So this is the book, or you can read Introduction to Lagrangian Mechanics by some Russian authors. Basically American physicists and those people have written quite a few books which deal with the basic introductory structure of this thing, formalism, and it is of great use in later courses of mechanical engineering, or for that matter engineering physics. So we let us be back with our problem. So we are dealing with a mass. Screen touch is crazy. Let us say this is solid platform, and let me say that there is a red block, and there is a spring attached to this block. Oh, it's horrible. I suppose it is ought to be better. Suppose there is a rigid support and there is some, like literally this is horrible. Okay, some kind of spring is attached. Spring has stiffness constant or spring constant K. Mass has, this block has mass M. Now I assume it is concentrated at the center of the block while it moves. So it is moving like this or in this direction. For that matter, now pause the video and think, what will be our generalized coordinate in this case? Will it be Cartesian? If it is Cartesian, will it satisfy the conditions of generalization? So far what we have done. So give it a pause and think about that. Obviously it is the easiest problem we can do, and our generalized coordinate we have chosen is x. Now ask yourself, is it complete? Yes. Is it independent? Yes. And does this pass the holonomicity test? Yes, because I have one coordinate to completely describe the system. And what is the number of degrees of freedom of this system? Well, the block can only oscillate to and fro, back and forth. So there is only 1 degree of freedom. We have chosen one coordinate, the two are equal. So by which I mean my coordinate which I have chosen is generalized. And now this support is fixed, rigid, spring is free to oscillate. So what's the kinetic energy of the system? Well, note that this is the natural position of the system. T, kinetic energy, is half m x dot squared. Right, x dot. We write half m v square. So basically it is half m x dot squared. There is a reason why I am writing everything in terms of generalized coordinates, because you have seen in the process of derivation of Euler Lagrange that we are working with the generalized coordinate and not with velocity or any other quantity like force or anything else. We are working with the basic generalized coordinates. So we write T, the kinetic energy of this system, as half m x dot squared. This is the total kinetic energy of the system. What is our potential energy? Well, give it a thought.